Hi, today I will be talking about some popular substrates for atomic force microscopy and scanning tunneling microscopy. If you have any question, you can contact me at this email address. So some popular substrates are mica, glass, HOPG, transparency sheets, silicon, gold-coated substrates, and there are many more possibilities. So each of these substrates have got their specific utilization, advantages and disadvantages. First, we talk about mica. Mica, as we know that it is layered material, and you can intercalate, de-intercalate some ions, etc., molecules inside the layers. So it can be exfoliated just by sticky tape. You can remove one layer, and then you have atomically flat, clean layer substrate, which can be used easily. My advice is that don't use it for force distance curve. This substrate is not very rigid, so it changes its property uh, when you press against this. So don't apply too much force because it changes its dimension uh, vertically because it's a layered material. So it's not very you can indent it very easily. But the advantages are that it's quite functional. So in aqueous medium, it loses its cations, and that leaves mica with a lot of negative charge and also a lot of functionality, and it is hydrophilic. So that makes it very interesting for biomolecules such as proteins, enzymes, and all kinds of cell. So you can have cellular growth, cellular attachments very nicely on mica. It is very good for cellular imaging, biomolecular imaging, and also for inorganic materials. It can be used, but as I mentioned, that it is not very rigid substrate. So you may get erroneous results when you are doing force distance curve. So next one is glass. I'm coming back to mica again. So mica has atomic smoothness for over several microns or maybe sometimes larger distances. So this is very good substrate, and it is cheap. Muscovite mica is most famous. I'll make a separate video on mica where you will get uh, details in depth. Next is glass. So you have two popular choices. You have borosilicate glass, which is cheaper. We use cover slips, and then you have fused quartz, fused silica, which are high quality um, glasses. Normally, glasses are not atomically flat. They have average roughness somewhere in nanometers. You'll be lucky if you find roughness better than this. But then glass is easily available, and it is good for if you want to attach some optics to your atomic force microscopy, so that can be done easily. And it is uh, it can be functionalized um, easily, and then you can use it almost at ease. It is slightly negatively charged, and it it is slightly hydrophilic. Next is highly oriented pyrolytic graphite. I'll make again a separate video on HOPG. So these are crystalline graphite sheets, highly packed, and it is atomically smooth, similar to mica. So you can peel off top layer, and then you have nice atomically flat region over micron area. So this is the substrate of choice for electrical measurements because it has very nice, very high electrical conductivity and thermal conductivity as well. And it has inbuilt calibration of that bonus because you can always look at the uh, carbon there, and you can calibrate. Same with mica. Mica, if you do a high resolution imaging, then you can calibrate your microscope using mica as well as HOPG. HOPG, the disadvantage is it is strongly hydrophobic, being carbon. So it is not, and it is very expensive substrate. It's not cheap. So it should be used for electrical measurements. Suppose you want to do some conducting AFM or some electrochemical measurements. So it is HOPG is a material of choice. The next is transparency sheet. It is easily available. You can cut it in any size, but be careful because it can bend. I mean, it is difficult to. It can just buckle actually, and then you may get some artifacts. So, but again, it is hydrophobic. So you have to choose those your sample if it is suitable. You have to look at the suitability of your chemistry of your samples. If it is fine, but it is also an option, and it is non-magnetic in nature. HOPG, all these substrates are non-magnetic in nature. Next is silicon, which is very famous. Silicon, you can take P-type and doped, heavily doped N-type doped. So you can play with the conductivity. So you can, in fact, do the conductivity measurements where you need to flow the current. Silicon average roughness is somewhere in few nanometers. I've rarely seen better than that. The problem is with this functionality. Silicon has always a top layer of silicon oxide. You can etch it away, but it gets easily coated in ambient condition with the thin layer, ultra thin layer of silicon oxide. So again, its surface roughness is somewhere around 2-3 nanometers most of the time. It can be functionalized. It can be functionalized using the silence, like APTES and aminosilins and mercaptocilins. So then you can attach some colloids, etc. So it has wider uses and acceptability, and it is quite rigid. So you can do your force distance measurements without much problem most of the time. Last is gold coated substrates. So here you can usually coat gold over silicon, so or glass. But gold does not coat easily on silicon or glass, so you have to put an underlayer of probably titanium or chromium, because gold does not wet silicon or silicon oxide. But gold coating on the substrate, you have to be careful because it can make the substrate. It can increase the surface roughness. Depends upon how you coat it, and but gold provides good functionality because gold makes nice covalent bond with thiols and amines. So here is a table which I have taken from Eaton West, the famous book on atomic force microscopy. So you can see in this table that mica, you can prepare this substrate by cleaving, and it is atomically flat. You can find angstrom level flatness. Common samples, almost all, especially single molecules. But I gave you already the warning that don't try to press it hard. Don't try to indent it. Don't do the force distance mapping because it's not very stable substrate. But it is chemically stable here. So cleave material, so you can cleave it. It's chemically stable, obviously. It has been there in the mines for billions of years, probably millions of years. It is hydrophilic, as I mentioned. HOPG is hydrophobic. It is also very stable material. You can cleave it. It's ultra flat, one of the flattest you can find, but it is expensive. It's acceptable for all the samples. especially single molecule spectroscopy you can do, but you have to check the it does not because it's being hydrophobic, so you have to see the chemistry of your samples with it, whether it is compatible or not. Silicon, or you can use it after removing oxides. Then this surface roughness varies from sub-angstrom to few nanometer, as I mentioned earlier. You can do lithography and electronic application. It is versatile substrate, and no doubt about that. Quartz or normal borosilicate slides. Roughness is pretty high here. You can see that, as I mentioned earlier, but it is suitable for many samples where you don't need ultra flat substrates. I'll mention it briefly. So in next video. So it is not very flat, but you don't need that. You don't need that high precision work all the time. So for routine purposes, glass is good, and it's available in large areas and fine. Last is gold coated substrates. So you can modify it chemically, and it's very easy to modify gold coating, and that gives it very nice uh, functionality and adaptability. Thank you very much.